back, folks. JLand Bio here for another exciting video on Chemistry 2. Today we are starting our focus on modern atomic theory. So what we're really going to focus on today is the concepts of light, energy, and Bohr theory. Now, this takes place to help you understand a little bit about how light, energy, and electrons truly function inside of the nucleus. So we're really focusing more towards a newer version of what the atom looks like. So let's go ahead and dive on in. Hopefully by the end of this video you should be able to explain the concepts of light and how it is related to modern atomic theory. You should also be able to calculate energy, wavelength, and frequency of an electromagnetic wave, and also be able to explain the Bohr model of an atom and how exciting an electron can cause an emission of light. We have quite a few new vocab terms here that are really focused on energy and light. We really are focusing more of a physics aspect of chemistry here, but still very important for us to know. So let's get to it. So what is light really? Well, light is a particle known as a photon, but light also exhibits wave behavior simultaneously. So it's very weird because it's one of the few, if not only, things that exhibit wave-particle duality. It travels through space at a rate of 3.00 times 10 to the 8th meters per second. We call this variable c. Weird, right? Light is weird, again, because it exists as both a wave and a particle. That particle is known as a photon. It's considered a small little packet of light. And what we say is that light is quantized. Quant mean number, right? So a certain amount of energy creates a photon. So that allows light to be a particle. Light is a wave because it's part of the electromagnetic spectrum. It has a wavelength and it has a frequency, wavelength being the distance between peaks, and frequency, how often the wave occurs. Now, we can categorize different colors of light by the wavelength and frequency as well. But the key thing to remember here is that light travels very, very quickly. It exhibits wave-particle duality, meaning that it exists as both a wave and a particle simultaneously, and that those particles are small little packets of light known as a photon. Now, again, light at different wavelengths appears as different colors. You probably remember the concept of Roy G. Biv, which are the colors of visible light going from the highest wavelength down to the lowest wavelength. Remember that light is just a small part of the electromagnetic spectrum. You have things like gamma rays, X-rays, ultraviolet, infrared, microwave, radio waves. Okay, those are different types of waves as well. But what we're really focusing on is light. And remember that light can be categorized into different colors based on the wavelength and frequency that's given by the electromagnetic spectrum. So what's really nice is that we can actually calculate the relationship between energy and wavelength using a formula, and it is given as E equals hc over lambda, where E is energy in joules, h is Planck's constant, c is the speed of light, and lambda is the wavelength. So like I said, what's nice about this is it's really easy for you to be able to go through and calculate the amount of energy that's in a wave, and vice versa. You can also calculate the wavelength. So let's dive in and take a look at a practice problem. So really quickly, what is the energy of red light with a wavelength of 450 nanometers? So with this equation, we're calculating the energy, we're given wavelength, we know we're going to be using the formula. Like that, okay? So the question is asking for energy, so that's our unknown. H 6.626 times 10 negative 34th, C 3 times 10 to the 8th. Now wavelength is a little bit weird because it's given in nanometers. It must be in meters. You know, C is meters per second, so we need to make sure that this gets converted to meters. Okay. Well, the easy way to remember that is that 1 nanometer is equal to 1 times 10 to the negative 9th meters. So we plug this in, it just simply becomes 450 times 10 to the negative 9th. Okay. Now, I know that that's not correct scientific notation, but for the purpose of the problem, we can go through and solve this relatively easily. Okay. So all we do, again, plug these numbers into our formula and solve. And what we get is an energy that is equal to, using correct significant figures of course, 4.42 times 10 to the negative 19th. Okay? And the unit for energy in this is joules. Okay? So again, just take your time, go through and calculate it. If I ask for wavelength, you'll get it in meters. I'll probably ask you to convert it to nanometers, so you will need to make sure that you know that conversion. All right, let's move on. So when we look at this new atomic model, we really are focusing on a new type of physics, and physics can be broken down into two separate parts. We have classical physics, which states that objects can have any kind of energy. But what we're looking at now is quantum physics, states that objects only have certain kinds of energies. Now this largely impacts how we view the concept of the atom, and more specifically how those electrons behave within that atom. So that's what we're going to take a look at, and a man by the name of Niels Bohr proposed a new model. He proposed that electrons travel around the nucleus very similar to planets around the sun. He suggested that orbitals get larger as the energy level increases. So if we look at the model here, energy level K would be the first energy level, L would be the second, M would be the third, and so on. The energy of an electron increases with that energy level, and each cell can hold 2 n squared electrons, where n is the energy level. So if you think about it, that kind of makes sense, because with the first energy level, you know that there is only a 1s orbital that holds a maximum of 2 electrons. Well, 2 times 1 to the second power is 2. Pretty straightforward. When we look at L, L would be the second energy level. You know that in the second energy level you have an s and a p orbital. 2 squared is 4 times 2 is 8. We have s plus p, 2s electrons, 6p electrons. That equals 8 as well. Even with the third energy level, we take 3 squared, and that gives us 9. 9 times 2 is 18. The third energy level, you have 3s, 3p, and 3d. S is 2, P is 6, D is 10, 10, 6, 2, 18. So the model still makes relative sense if we think about it today. Now there are a few gaps in the model, but we won't focus on those at the moment. Bohr expanded on the periodicity concept that was given by Mendeleev. He really focused that each outer valence shell with a group has the same number of valence electrons except for H and He. Notice the increase in the n value as well. So lithium and sodium are in the same group. Notice that the number of valence electrons, that is the number of electrons on the outermost orbital or outermost valence shell of the atom, is 1. They are the same for both of them. And as you go down, you know that all of those in that first group contain just simply 1 valence electron. So Bohr just really expanded on Mendeleev's key concepts here. Now, Bohr was also successfully able to determine the amount of energy required for the electron to jump an energy level from the ground state to an excited state. So the electron that is found in hydrogen is at the very first energy level. Okay? If you add energy to that electron and you excite that electron, it can actually jump to the second or third or fourth, fifth, or sixth energy level, simply depending on how much energy you add to make that happen. Notice the trends here. When we go from the first to second energy level, it requires an enormous amount of energy. First to third requires more energy, but the jump between 2 and 3 is significantly smaller. Same with the jump between 3 and 4, 4 and 5, 5 and 6. Okay? This tells you a little bit about how much energy is required to get that electron to be able to jump those energy levels. So do keep that in mind, that we can pump energy into an electron and cause it to jump, to go from the ground state, the original state, to the excited state. Now, again, keep in mind that the amount of energy required for the electron to jump from 1 to 2 is the largest jump. Jumps for each successive energy level actually decrease. Once the electron actually drops back, so that energy is released as light. And light is related to the energy of the photon that is released. So if we look at the amount of energy that's present in that particular photon, that tells you what color of light is actually going to be released from that spectra. So different elements are going to have different spectra based on how much energy is required to cause that electron to jump that energy level. As it releases that energy and comes back down to the ground state, it releases that energy as light, and that's where we get atomic spectra for. So if you look at the bottom here, we have atomic emission spectrum for hydrogen. And you can see that if it goes from the 6th energy level to the 2nd energy level, it emits a violet light. If you go from 5 to 2, it emits more of kind of a dark bluish, 4 to 2, light blue, almost a green, and 3 to 2, a reddish orange color. Okay, this is also the key concepts for how neon lights are created. Energy is pumped through a gas tube that is full of neon, which excites those electrons that are in neon. When that energy, that electron goes from the excited state back to the ground state, it then releases that energy as light, which is why you see all of the pretty colors that exist in neon lamps. So just some practical application of what we're talking about. Hey guys, that's all I got for this video for today, just to give you a basic understanding of electrons, energy, atomic spectrum, and the Bohr model. We will talk to you guys later. Have a great day. Take care. Bye-bye.